Okay, welcome to the operations research course. For this course, we'll look at network scheduling. So under the network scheduling, we shall look at the concept of CPM, what we mean by PERT network. Then we'll look at how to schedule an activity and uncertainties in activity times, that is the PERT. And we'll look at how to crash a particular project so we can complete it in the shortest possible time. Then we'll also solve some problems. So let's see what we mean by network scaling. So network scaling actually helps in planning a very large complex projects, right? And also scaling and controlling, having management control on a very large complex projects. Typical projects will be installation of a refinery, oil refinery or gold processing plants. So you see that it's a very big and a complex project, and therefore it needs a strategic, systematic way of completing it. So usually two best known techniques are available. That is the CPM, which is the critical path method, and a project review and evaluation technique, PERT, or it can also be project evaluation and review technique, right? So both are identified with respect to their basic concepts, right? For instance, the concept focuses on activities, focuses on events, predecessors, and the critical parts, right? But when we talk about PERT usually emphasizes on uncertainties, that associated with a typical activity. Like for instance, an activity must be completed in 2 minutes, but we are not sure whether we can complete it in exactly 2 minutes. So the typical way we say we can complete it between 1 to 3 minutes, that means that averagely in 2 minutes. The worst case is 3 minutes, then the best case is 1 minute. So that's a typical way of representing uncertainties which PERT captures. However, the critical path method, the CPM, assumes certainty with regard to activity times, So, and also it's regards to the estimates. So we are actually certain about activity time. Our estimates are usually much accurate in terms of the CPM, and much emphasis is placed on project costs and completion time. So you see that PERTs, right, has often been used to plan and control research. Why? Because most research, we actually have an idea, a concept, but we don't know how, the research will go. So usually PERT is used because most research have a lot of uncertainties, right? However, CPM are more frequently used for large construction projects, large construction projects, but both, ensures that they both ensures that the activities are scaled in a systematic way, right? And therefore they can be applied in shipbuilding, highway construction, right, refineries, major building projects, installation of various machinery, right? So when you look at mining, the mining industry, right, the CPM and PEM are used for construction and installation of shovels. So usually a shovel comes to site or an excavator comes to site, and we assemble the excavator on site, drag lines, conveyor systems, hoist machinery, right? Even if we have underground stopes that we want to mine, we want to extract the ore, we can use the CPM or the PEP to schedule that, right? And also other various production activities, like we want to look at drilling, operation, blasting operations, so we can do all these things using the PERT or the CPM. So what is the concepts? There are two major components of CPM and PERT network. Yeah, and activities and events. So an activity is an operation or process consuming time and resources, and usually comes with costs, right? However, an event is a state. It's a state in the progress of a project after the completion of all the preceding activities, but before the start of any succeeding activity. So it is required that the CPM or PERT network modeling process, it is required that they are broken down into processes, right? Where we have independent activities or what we refer to as jobs or tasks. And these activities will now specify precedence, relationships, So we have several activities and we know which comes after the other or which comes before the other, right? So let's look at a typical example here. So the University of Mines and Technology has planned to construct a concrete walkway from the library to join the main road, to Government Hill. So this involves the following activities. So there are two main activities here. Activity one, starting from, we have one start node to two finish node, right? Then when two is completed, then activity B starts. So we start from two and ends on three. So the activity description now, the activity one is we are constructing wooden forms, all right, or forms, what we say in the construction system or in the construction industry. We construct forms or we use wood to construct the skeleton of the structure, right? And it can take 5 hours. Then we pour concrete. Then you see that activity B, right, has a predecessor of A. That means that A must be completed before B must be started. So this typical construction is in this form. So we first have a node, which is 1 to 2, and A is the activity, right, between the jobs or between the tasks that must be completed. Then B, we then pour the concrete after that. So you see that we have three events, right? We have three events. The start event, construction of form done, and then concrete has been poured, right? So usually we have node 1, node 2, and node 3 representing the event positions, right? So the events are represented by nodes and activities are represented by arrows, right? So the direction of the arrow indicates the direction of the activity proceeds, right, where the activity is moving. So the length of the arrow is not proportional to the duration of an activity, right? Also, the network shows that activity A precedes activity B, or activity B succeeds activity A. All right. So the network can be drawn in several ways, right? For instance, we can have two tasks, or two activities coming from two different jobs or nodes and ending on one node, which is okay, right? It can come from one node to another, which is also correct. An activity can come from this, you should always have the arrows. And we can also have one activity, one job or task or event or node, however, two activities coming out from that node. And that's also correct. And we can have a combination of the network. So in all the networks above, the jobs A and B are concurrent, so they are happening at the same time, right? So you can see that this and that, they are happening at the same time. right? And activities A and B should be completed before activity C. That is when you look at this aspect of the diagram or the network, right? What are dummy activities? So there is a need for dummy activities when the project contains groups of 2 or more jobs which have common predecessors. So if they all have the same predecessors and also the same successor, then we'll say that there is a need to create a dummy activity. What does that mean? So the dummy activity has no duration and it does not consume time. So for instance, I have so I have node 1 and I have node 2 and I have activity A and I have activity B following like that. So something like this is not correct. It is incorrect, right? So you cannot have the same 2 different activities having the same node and the same start node and the same end nodes, right? If that is so, then you need to create a dummy activity. We'll look at an example for us to appreciate what we are referring to. So let's look at our form construction and the concrete pour, the University of Mines walkway, concrete walkway, right? So to demonstrate the use of dummies, right, the side walkway construction project, right, we can modify it and say that we need to prepare the concrete before we can construct the forms, and also we can pour the concrete thereafter, right? So you can see that during the preparation of the concrete and during the construction of the form, they can all happen at the same time. That means that we can have 1, we can have 2, and we say that this A prime is for preparing of concrete and A is for construction of the forms. However, because these 2 are 2 individual or independent activities, they cannot have the same start node and end node, and therefore representing the network in this way is wrong, and then we need to introduce a dummy. So that is why we say that A prime and A, right, they have the same start node. However, we'll have a dummy connecting the A prime and the A, together. And the arrows might just lead to the final arrow that of the activity that succeeds it, right? So this is how it is, right? So this dummy actually is not consuming any time, it's not consuming any resources, right? It has no duration, but it helps in representing the tax, accurately, right? Set in representing the tax accurately. All right, so the network could also be constructed as follows. So this is how what I represented earlier on, right? But because we can have 2, which will violate the basic rule of the CPM PERT modeling, right? That is 2 or more network activities cannot simultaneously share the same start node and the same finish node, right? So a dummy activity is therefore created to resolve this. So a dummy activity, which is the job, has a broken arrow and is used to preserve the precedence relationship in the network, the precedence relationship in the network. All right, so we can look at this typical example here and see how we can construct such an activity. So let me bring the whiteboard and let's do this together. All right, so we have the whiteboard here. So we have an activity and the activity is, we have activity A followed by B. So let's assume we don't know how this is. So we have node 1 and we have node 2, and between node 1 and node 2 is an activity A, right? And it says that activity A is followed by B and C. So let's say I have node 3 and node 4. And never worry, someone can have different nodes, different name. The nomenclature is not that very important. It is the activity that consumes time and resources, and they are more important. So A is followed by B and C and preceded by nothing. Now, activity B is followed by D. Activity B is followed by D. So when I put 5 here and I put D here, yeah, so this one means that activity B is followed by D. However, it says that activity B is preceded by C and A. It's preceded by P, by C and A. That means that the arrow from C should be entering B, right? That means that the arrows from C should be entering B. However, B, remember C is also coming from or is following A. So what this means is that we need to, when you create this activity, you turn the arrow in this way, right? Meaning that the business of C is A. So there is a dummy that must be created, right? There is a dummy that must be created. So we will change this and we'll represent it with a dummy. Now, certain problems. So certain problems are written in such that the node which must correspond the task or the job are actually used to represent the activity, and therefore such problems, when you are constructing the network and you are seeing some of these things, like for instance, C is followed by A, and now C has only precedence of A, then it means that this is the nature of the problem that has been created, right? So we shall represent the node here with the activity. So we shall suspend this, but still leave it tight, and let's use the node as an activity. So we have A followed by B and C. So followed by B, followed by C. Then we have B followed by D. So you see how easy this goes. B followed by D, and the precedence and preceded by C and A. C and A. So it means that there is supposed to be a dummy here. Supposed to be a dummy here. All right. Then we have C followed by C and A. So we have C followed by E and B, followed by E and B. Then we have E followed by G and F, followed by G and F. So it means that we need F here, we need G here. It doesn't matter how you do this, but later on you'll see. D is followed by F and preceded by B. E is followed by F and G, preceded by only C. So this is correct. Then F is followed by H, preceded by E and D. So it's H preceded by E and D. Then G is followed by H and I. And preceded by E, which is correct. Then we have H followed by I, preceded by G and F. Then we have I, which is not followed by anything, so that the last activity or the last load, and preceded by G and H, by G and H. All right, so let's see the dummy, whether it's really a dummy. So we have activity A followed by B and C. Yeah. Activity B followed by only D, preceded by C and A. C and A. Yeah, we'll use a dummy for the meantime. Activity C followed by B and E. So let's make it a full activity. Yeah, a full activity here. All right, then C followed by E and B, yeah, preceded by only A, yeah, which is correct. D followed by only F, yeah, preceded by B, yeah. E followed by G and F, preceded by C. F followed by H, preceded by E and D. Then G followed by H and I, preceded by E, and H followed by I, preceded by J and F, and I followed by J and H. All right, so this is the activity schedule for this typical example. So when you try to code this using the node, you realize that we'll have several challenges based on the precedences that we have, right? So in this a typical example, when the node is represented by an activity, right? The node is represented by an activity. All right, so we shall go back to our slides. We'll close this whiteboard and go back to our slide here. And we will look at this. So what then is a critical path? So the primary objective of the CPM PERT is to determine the minimum time. Required for completion of a project. So the minimum time required to complete a project is equal to the longest time path or sequence of connected activities through the network, which describe the precedent relationships of all project activities. So the longest time path is also the critical path. So here, for us to determine the critical paths, if you add 2 to 0 and 1, we have 2 plus 0 plus 1, and that is 3. If we have 5 and 1, then it will be 5 plus 1, and that is 6. So this is our critical path. So usually, if you identify the critical paths, you draw another line along the activity or the arrowed line to indicate that is a critical part in the problem. So the critical part for that example is 6 hours. That means that it is the longest time to complete the activity, right? And it should be noted that activity A prime, which is the preparation of concrete, right, completes in 2 hours, but activity B can only begin after activity A. That's construction of the form is complete. Therefore, there is a 3-hour, that is 5 minus 2 slack or float associated with this activity. So that means that if you want to delay activity A prime, you can delay it as much as 3 hours. That's what it means. Can delay as much as 3 hours. So it is actually necessary to determine the activity schedule that gives the start and finish times of each project activity. So in preparing such schedule, right, a framework is provided for determining the critical path and duration of the project. So the schedule for a typical conveyor system acquisition and installation is provided in this table. So when the duration of activities are known, the next step is to show the start and end event notes of each activity using the other pieces of information to given to construct a network. So this is a typical activity schedule for typical activity that might be scheduled for a conveyor system, acquiring a conveyor system and also installing it. So we have all the various activities from A to M, and we have activity precedences and we have duration, for each activity. So we first want to order or purchase the various system components, right? And we'll use 1 day, then we'll arrange for shipping. We'll ship the components to the harbor, prepare the sites, where we'll construct the conveyor system, transport the components from the harbor to site, pour concrete in place for foundation, install and support structure, deck, and all those things. Then finally we test run. So if we look at this activity, then we'll see that we have the start node and the finish node also given and the predecessors, right? So if you are to construct this activity, this will be the typical table. So we have activity A, which is from node 1 to 2, right? And the consuming time is 1. Is the duration is 1. Then we have activity 2, or B, right, which the duration is 2, and it runs from node 2 to 3. So we construct this network, right? So as you can see, the network shows the precedence and relationships and the duration of each activity. So in order to determine the critical part of the projects, right, the concept of earliest time and latest time will be presented. All right, so we'll be looking at earliest time. What do you mean by earliest time? ET. So earliest time is the point in time, at which all activities leading to a particular load or event are completed, right? So earliest time, ETI, right, where I is denoting the node number, right, is therefore the earliest, is the earliest starting time for all the activities emanating from the node I. So the earliest time values for each event are calculated by a forward pass through the network, progressing from the project start node to the end. So since node 1 is the initial project event, in the conveyor system, then the ETI, or which is ET1, is always 0. That's the initial one, right? So the earliest time for event 2 is the completion time of the activity 1, 2, which is 1, and so on. So we shall take an example and we can calculate that, right? However, when you have an earliest time, we have 2 particular nodes. Let's say for node, let's say for node 4 or node 6, right? For node 6, right? The earliest time is coming from this node 4 and also node 5. So what we do is that we calculate the earliest time and we pick the largest value and we slot it as the earliest time. So this is what we do. So the earliest time is usually the max of the earliest time of that node, plus the activity that is coming in on that node, right? So if, for instance, we look at the earliest time for node 6, so it's actually the maximum earliest time for node 4 plus the activity T46. So that's the activity from 4 to 6, from node 4 to 6, right? And the activity earliest time node 5 plus the activity 5 to 6. So the largest will now be the earliest time. So how do we compute this? So the earliest time here is 0. Then on the node 2 is 1, right? On the node 2 is 1. Usually we put the earliest time in a box. On the node 2 is 1. On the node 3 is 1 plus 2, which is 3. On the node 4, so I can delete the value here. On the node 4 is 3 plus 4, which is 43. Then before calculating that for node 6, I need to recalculate this line. I need to recalculate this line or this leg. So from 1, activity here is 1 plus 32 is 33. Then even here, 33 plus 0 is 33. But we pick the max, so 43 is still correct. So here we have 33 plus 15, and this will be 48. Then we have 43 plus 1, and this will be 44. And the earliest time is the max of either this or that. So it's 48. So 48 comes here. The earliest time here will be 48 plus 10, which is 58. The earliest time here will be 58 plus 1, which is 59. The earliest time here, I have to hold on and calculate this leg. Earliest time is always on top. So 58 plus 12, that will be 68, that will be 70, right? That will be 70. Then 70 plus 1. So I have 51 plus 1, I have 60. 70 plus 1, I have 71. What about here? 58 plus 3, I have 61. So the largest is 71. So I put 71 here. Then the final one will be 71 plus this activity 3, and that is 74. All right, that will be 74. So when you compute this, you see that we have the earliest time 74, right? Then later you compute the latest time. The latest time is put under it. You always start from the back or from the last node in the system. All right, so let's attempt to do this on this small network that we have. Let's use a different color. Let's say blue. So let me put this here. So what I have here is 74. Start with 74, like the way we started with 0 here. Yeah, 74. Then 74 minus 3 is 71. Then for this node, 71 minus 1 is 70. This is converging from 3. So I have 71 minus 7 minus 3. 71 minus 3, that will be 68. So I have 68 here. Let's calculate this. 71 minus 1 here is 70. All right, so 70 minus 1 is 69. Then 70 minus 12 is 58. So here we actually, for the latest time, right, we actually take the minimum value. So that will be 58. 58. Then we have this. It's computed by 58 minus 10 is 48. 48 minus 15, 33. 48 minus 1 is 47. 47 minus 40 is 7. 7 minus 2 is 5. 33 minus 32 is 1. So the minimum will be 1. Then 1 minus 1 is 0. So this is the latest time, right? And usually to get a critical part, it's just the activities that have the same earliest time and latest time. So we have this, so I have double line here in the critical activity, 70, 70, I have that. 58, 58, I have that. So I'm just doubling the lines. 58, 58, 58, then 48. So this line, 33, 33. So this node to this node is the critical activity. 1, 1 is that, then that. So the critical part is actually node 1, 2, node 5, node 6, node 7, node 8, node 10, and node 11. What is more important is the activity. So activity A, D, F, G, H, L, is K, S, K, K, then M. So these are the activities. But let's move on and let's see. We'll look at these things in details. So the latest time is used to determine the critical paths, right? So the latest time is the latest time an event can occur without delaying the completion of the project. So the latest time values for each event are calculated by a backward pass, right? Starting from the last node to the first node. So on a network, the earliest times are indicated in rectangular boxes on top, while the latest time are indicated by triangular boxes. Right. So if you should calculate the earliest time and the latest time, we'll have this, which you already calculated, right? So 1 and 33, 48, 58, 70, 71, 74. So the critical part actually lies on the node where the ET and the LT are equal. It is shown by a double line. So you can see the double line in this network. All right. So the critical part is A node 1 to 2, 5, 6, 7, 8, 10, and 11. So the critical activities and critical events are those lying on the critical parts. Right. So what is activity slack? Activity slack is a measure of how much a non-critical activity may be delayed or extended. Right. So it can be realized from the network that the non-critical activities can be delayed to some extent without delaying the completion of the conveyor project. Two types of slack are available for each activity. So we have a total slack, which is also called float, and also free slack. So total slack is always greater than or equal to the free slack. So the free slack is always less than or equal to the total slack. Okay, so total slack for any activity is the maximum time period available to schedule the activity minus the estimated duration of the activity. So the total slack here for a particular activity is given as the latest time of the activity G minus the earliest time of the node minus the TIJ. That's the activity duration. Right. So for this, we have to tests all the non-critical activities. So the non-critical activities here will 3, 4, load 3, 4, and 9. So the activities itself will be B, C, E, I, and L. So that means that we have 4 slack, total slack to compute, right? Or a free slack to compute. So if we look at this, then we can compute. Let's take, for example, 7, 9. That is activity I. So activity I. So if we look at activity I, which is 7 to 9, there is the earliest time on the 9 minus the earliest, the latest time on the 9 minus the earliest time on the 7, right, divided by minus the activity time. So 70 is the latest time. It's always triangular. Minus 58, which is the earliest time on the node 7, which is the one in the rectangular box, minus the 1 activity, and that is 11 days. So it means that the total slack, right? So the activity I can be delayed for as much as 11 days. What this means is that if the activity I, which is representing the installation of the loading and discharge chutes, if there are issues with the labor, with any issue on the project, right? Then as much as you can only delay that activity for 11 days. That's what it means, right? That's what it means. Assuming we want to also look at 9 and 10, right? How far can we delay activity L? So activity L, right, is actually from node 9 to 10. So from node 9 to 10, the latest time for the node 10 minus the earliest time for node 9 minus the activity 9, 10 is also given by 71. So the latest time here, 71, minus the earliest time, which is 59, minus the 1, right? And that's also giving us 11 days. So similarly, the activity 9, 8, 9, 10, which is activity L, right, can be delayed for a total of 11 days without affecting the completion of the project. So this is the total slack. So the free slack is the slack associated with an activity, said that if the activity is delayed by such period, it will not cause any delay in its immediate successor activity. So the free slack looks at the impact on the next activity, right? So it is actually given by earliest time of the succeeding activity minus earliest time of the previous node minus the activity, right? So if we are to assess the 7 and 9 activity, which is the activity I, right, then the free slack here is computed as 0, meaning that so far as we delay that activity, right, is going to affect the next activity. So how much can we delay the activity so that it doesn't affect the next activity? It's actually a 0. There's no way we need to delay that. If you delay that by a day, it's going to affect the critical part or the completion time. What about activity 9 to 10? So the activity 9 to 10 means that the earliest time of 10 is 71. The earliest time of activity on the node 9 is 59, and the time of the activity consuming time is 1. So the earliest time, the free slack is actually 11. What this one means is that we can delay activity L. We can delay activity L by, okay, so this one was actually J. This is J, and this is I. Can delay activity L by 11 days before it will affect activity M. This is what that is, the free slack. So the free slack in the system is just affecting the succeeding activity. So a complete computation of the ET, the earliest time, latest time, free slack, and total slack is presented in table 5.8. So we have that here. So we can have all the earliest time and the latest time here, the total slack and the free slack. So you see that there's a dummy, the E, activity E. So activity E is actually, let's practically look at what activity E is. Transport component from harbor to site. So we can delay that for as much as 4 days before it will affect the next succeeding activity. Same with activity L, that is connecting the motor to the main electric supply. So assuming they are permitting delays in terms of getting electricity, there are challenges, then we can as much reduce delay the activity by 11 days before it will affect the next activity, which is the testing run, before it will affect it. Yeah, so that is that for this typical example. So uncertainties in activity. So we'll look at this in our next lecture, where we'll look at using the PERT instead of the CPM, which assume uncertainty. So thanks for joining me, and hope to see you in the next lecture. Bye.